In May 2019, something hit our detectors that physicists are still arguing about today. A ripple in space-time so strange, so structurally wrong, that 6 years of analysis have failed to fully explain it away. It came from across the universe. It lasted less than a tenth of a second. And in 2025, a team of researchers published a paper suggesting that the most accurate description of what we actually recorded that day is this. We may have picked up an echo from a collision that happened in a completely different universe, a signal that punched through a wormhole and arrived here in our instruments on an ordinary Tuesday morning without any of us knowing what we were looking at. That is not science fiction. That paper was published by researchers at the Hangzhou Institute for Advanced Study at the University of the Chinese Academy of Sciences. It passed through peer review. It sits in the scientific literature right now with a conclusion that the data cannot definitively rule out. And when you understand everything that has happened in wormhole physics since that signal first arrived, the idea stops sounding impossible. It starts sounding like something we may have genuinely stumbled into without realizing it. The signal has a name. It is called GW1990521. The GW stands for gravitational wave, and the numbers are the date of detection, the 21st of May 2019. It was picked up by LIGO, the Laser Interferometer Gravitational Wave Observatory, which is one of the most sensitive instruments ever built by human hands. LIGO works by firing laser beams down 2 perpendicular tunnels, each 4 kilometers long, and measuring with extraordinary precision whether those beams arrive at exactly the same moment. When a gravitational wave passes through, it stretches and compresses space itself by amounts smaller than a fraction of a proton's diameter. LIGO catches that. It has been doing so reliably since the first confirmed gravitational wave detection in 2015, a discovery that earned its lead scientists the Nobel Prize in Physics in 2017. By 2019, LIGO and its European partner Virgo had detected nearly 100 gravitational wave events. Almost all of them came from one of 2 kinds of collisions, either 2 neutron stars spiraling into each other or 2 black holes merging into one. Scientists can tell the difference because each type of collision produces a signal with a distinctive shape. When 2 black holes approach each other, they go through a specific 3-part process, and each part leaves a recognizable mark on the gravitational wave they send out. The first part is the inspiral. As the black holes circle each other, getting closer and closer, their orbits shrink, they speed up, and the gravitational waves they produce grow stronger and faster in a rising pattern. If you convert that pattern into sound, it sounds like a rising chirp, which is exactly why physicists use that word for it. Every binary black hole merger humanity has ever detected begins with this chirp. Then comes the merger itself, the instant of collision, which produces the sharpest, strongest peak in the signal. And after that comes the ring down. The newly formed black hole is not perfectly spherical right away. It wobbles, it oscillates. And those oscillations produce gravitational waves in 2 distinct frequencies, both of which fade out over the course of a few tens of milliseconds as the black hole settles into its final shape. Inspiral, merger, ring down. That is what every black hole merger signal looks like. It is consistent, it is reliable, it is one of the clearest patterns in all of observational physics. GW1990521 was missing the first part entirely. There was no inspiral, no rising chirp. The signal appeared out of nowhere, produced its peak, and then went through a ring down at 2 distinct frequencies, 63 Hz and 98 Hz, before fading out completely within about 28 milliseconds. The whole thing lasted less than a tenth of a second. The standard model said this should have been impossible, or at least deeply anomalous, because at the mass involved, the inspiral phase should have been well within LIGO's detection range. The black holes that produced this signal were calculated to weigh 85 and 66 times the mass of our Sun, respectively. They merged to form a single object 142 times the mass of the Sun. 9 solar masses worth of material vanished in an instant, converted entirely into pure gravitational energy that rippled outward across the universe for over 17 billion light years before reaching Earth. And the inspiral that had to precede all of that was simply not there. Physicists spent years trying to find the inspiral in the noise. They tried every analytical method available. They looked at the data from every possible angle. Nothing. The signal started where it started, with no warning, with no characteristic buildup. And in September 2025, a team led by researcher Qi Lai at the Hangzhou Institute for Advanced Study decided the most honest thing to do was to take the weirdness seriously and follow it wherever it led. What they proposed was this: 2 black holes in a parallel universe, a universe that exists somewhere beyond our own in whatever geometry the multiverse actually has, spiraled together and merged normally. That merger produced the standard 3-part signal. But the merger did not leave behind a simple black hole. Instead, the immense energy of the collision created a wormhole. One end of that wormhole opened in the parallel universe. The other end opened here, in ours. The inspiral and merger phases of the signal stayed in the universe where they happened, but the ringdown, radiating outward in all directions from the newly formed wormhole, sent some of its waves down through the throat of that wormhole and into our space. Those waves arrived at LIGO as a sudden isolated burst with no inspiral preceding it, because the inspiral had never happened in our universe at all. We heard only the echo, the tail end of something that began somewhere we can never see. When the team ran the math on this model, the result was striking. The wormhole echo model produced a signal-to-noise ratio in the detectors that was statistically comparable to the standard binary black hole merger model. Not identical. The conventional explanation still fits the data slightly better by Bayesian analysis, but the margin is small enough, according to the authors, that the wormhole hypothesis cannot be dismissed. The paper uses the phrase "cannot rule out." In physics, that is a significant statement. It means the data is genuinely consistent with something that most scientists would have called impossible 5 years ago. To understand why this is even theoretically possible, you need to understand what wormholes actually are. They are not science fiction inventions. They arose directly from the mathematics of general relativity, Albert Einstein's theory of how mass and energy curve spacetime. Einstein himself, working with physicist Nathan Rosen in 1935, discovered that his field equations permitted a geometric structure that connected two separate regions of spacetime through a kind of bridge. This became known as the Einstein-Rosen bridge. Einstein and Rosen did not invent it as a creative speculation. It fell out of the math whether they wanted it to or not. The equations described it. It was real within the framework of general relativity. The only question was whether it could actually exist in nature, and if so, whether anything could pass through it. The early answer to that second question was discouraging. The Einstein-Rosen bridge, as originally described, is a one-way structure connecting a black hole to a white hole. A black hole is a region of spacetime from which nothing can escape once it crosses the event horizon. A white hole is the mathematical opposite, a region from which things can only exit, never enter. They are time-reversed versions of each other, which follows naturally from the fact that Einstein's field equations work the same whether time runs forward or backward. The Einstein-Rosen bridge connects these two objects, but the mathematics says the bridge collapses so instantly that not even light could travel through it before it snaps shut. So in its original form, a wormhole is real, but completely unusable. Then, in 1988, astrophysicists Michael Morris and Kip Thorne asked a different question. Instead of accepting that wormholes collapse, what would it take to hold one open? Their answer was exotic matter, not antimatter, which is real and has positive mass, and is produced in particle accelerators every day. Exotic matter is a theoretical category of material with negative mass or negative energy density. Normal matter attracts other matter through gravity. Pull a book toward yourself and it comes toward you. Exotic matter would do the opposite. Push it and it accelerates away from you. Apply gravity and it moves away from the gravitational source. This repulsive effect is exactly what would be needed to prop the throat of a wormhole open against the crushing gravitational forces that would otherwise collapse it. Exotic matter, if it exists, would act as the scaffolding that keeps the tunnel stable long enough for something to pass through. The laws of physics do not explicitly forbid exotic matter. It violates no conservation principle. It has never been observed, but its existence is technically permitted by the math. And in the quantum world, something called the Casimir effect has already demonstrated that negative energy density can exist in small quantities between closely spaced metal plates, where the geometry of the space between them allows certain quantum fields to produce a net negative energy. Whether this scales up to anything capable of holding a cosmic wormhole open is a question without an answer yet. But the theoretical door is not closed. What has happened more recently is something even more fundamental. In 2013, theoretical physicists Leonard Susskind at Stanford and Juan Maldacena at the Institute for Advanced Study put forward a conjecture that attempted to bridge the two biggest theories in physics. General relativity describes the universe at its largest scales, the fabric of space-time, gravity, black holes, the expansion of the cosmos. Quantum mechanics describes it at its smallest, the behavior of particles, the probabilistic nature of measurement, the strange correlations between entangled systems. These two theories are both extraordinarily successful. They are also deeply incompatible. At the center of a black hole, where both would need to apply simultaneously, their mathematics produces nonsense. They cannot both be fully right in the same place at the same time, and nobody knows exactly where the breakdown occurs. Susskind and Maldacena proposed that the answer to this incompatibility might lie in a connection nobody had previously suspected. They suggested that quantum entanglement and wormholes might be the same thing. When two particles become entangled, they share a connection that cannot be explained by anything traveling between them. Measure the spin of one particle and its entangled partner, wherever it is in the universe, instantly snaps into the corresponding state. No signal passes between them, no information travels. The correlation simply exists instantaneously, regardless of distance. Susskind and Maldacena proposed that this correlation is not just an abstract mathematical relationship. It is a physical one. The two entangled particles are literally connected by a geometric structure, a tiny wormhole running through the fabric of spacetime that links them directly. Their conjecture is known as ER equals EPR, named after the two papers from 1935 that described, separately, the Einstein-Rosen bridge and quantum entanglement. The claim is that these two things are not separate phenomena. They are the same phenomenon viewed from different levels of description. Testing this conjecture is extraordinarily difficult because the wormholes it describes are microscopic, and the systems involved are deeply idealized. Critics pointed out for years that ER equals EPR had only been demonstrated mathematically for perfectly idealized scenarios. Two black holes in perfect thermal equilibrium with perfectly smooth, symmetrical interiors. Real black holes are nothing like that. They are chaotic. They receive infalling matter constantly. They are buffeted by quantum fluctuations. If the conjecture only held for systems that do not exist in nature, it was not much of an explanation. In October 2025, a team of physicists published a study in Physical Review Letters that changed this. Researchers Javier Magin, Martin Sasieta, and Brian Swingle examined what happens to the wormhole connecting two entangled black holes when you make those black holes realistic, when you make the quantum entanglement messy, random, and chaotic the way it actually is in nature. What they found was unexpected. The wormhole did not collapse. It did not become unstable. It did not stop being a wormhole. Instead, it became something they named the Einstein-Rosen caterpillar. As the chaos of the entanglement increased, the wormhole grew longer and bumpier. It developed uneven bulges and irregular segments along its length, like a living creature made of quantum matter. It became more complex, more distorted, and harder to describe cleanly. But it remained a geometrically stable structure through which the classical laws of gravity still held. The more chaotic the quantum state of the black holes, the longer and stranger the caterpillar connecting them became. And the firewalls that had been predicted at the event horizon of black holes, destructive walls of infinite energy radiation that would incinerate anything approaching, did not appear in their models at all. The caterpillar exists, it grows, it deforms, but it persists. Then there's the quantum computer experiment from 2022 that the scientific community has not stopped discussing. A team led by Maria Spiropoulou at Caltech used Google's Sycamore quantum processor to build a model of two entangled quantum systems, and, using the principles of the ER equals EPR conjecture, successfully sent a quantum bit of information into one side of the system and recovered it on the other. The information diffused from its starting particle across the entire system, like a drop of dye spreading through water, and then reemerged on the opposite side, reconverging onto a single particle, the entangled partner of the one it started from. Information went in one side and came out the other. The team described the experience as comparable to witnessing the first data from the Higgs boson discovery. The physics community urged caution, correctly noting that the quantum model was far too simple to be considered a true reproduction of a black hole in nature. But that is not what the experiment claimed. What it demonstrated was that a quantum system governed entirely by quantum mechanics can behave in a way that is mathematically identical to a wormhole in a gravitational theory. The physics of both regimes, the tiny and the cosmic, look the same when you look at them through the right framework. Now bring all of this back to the signal that started this story, GBSU-1905221, detected on a Tuesday morning in 2019, missing its inspiral. Too short, too strange. 6 years of analysis, unable to fully explain it. A 2025 paper proposing that what LIGO detected was the ring down of a black hole collision in another universe, transmitted through a wormhole created by that collision, received here as an isolated echo with no preceding buildup, because everything that preceded it happened somewhere we cannot see. For this to be true, two things must hold. First, wormholes connecting entangled black holes must be real and stable enough to transmit a signal. The Einstein-Rosen caterpillar says yes, at least in principle, even under chaotic conditions. Second, information must be capable of traveling through such a structure. The Caltech quantum computer experiment says yes, at least mathematically. Neither of these is a definitive proof in the context of cosmic black holes billions of light years away. But they are the closest things to proof of concept that physics currently has. And the Chile paper confirms that when you model what such a wormhole-transmitted signal would actually look like in a gravitational wave detector, it produces numbers comparable to the standard explanation for the same event. There is something worth noting about the 2023 detection called GW231123, the most massive gravitational wave event ever recorded, involving a final object of 225 solar masses. The Chi-Li team pointed out that this event shares the same strange characteristics as GW-99051, a burst-like, short duration signal without the expected inspiral. If two separate events with the same unusual properties exist in the data, the probability that both represent the same exotic phenomenon grows, not conclusively, not provably, but meaningfully. LIGO and Virgo have been operating since 2023 with 30% greater sensitivity than before, detecting a merger roughly every 2 to 3 days. The volume of data accumulating is unlike anything the field has ever had to work with. As that data grows, the statistical picture of how common these anomalous short-duration signals are will become clearer. If they cluster, if they share patterns, if the wormhole echo model consistently fits a subset of detected events, while the standard model struggles with those same events, the hypothesis moves from possibility to something that demands experimental confrontation. We are at a genuinely strange moment in the history of physics. The mathematics has been saying for 90 years that wormholes are possible. The ER equals EPR conjecture says they may be inseparable from quantum entanglement itself. The Einstein-Rosen caterpillar says they survive chaos and remain stable in realistic conditions. The Caltech experiment says information can traverse them. And a real gravitational wave detected in 2019 has a shape that does not rule out the possibility that it came from somewhere beyond our universe through one of these structures. None of this is a confirmed discovery. The scientists involved are careful about that. The paper does not claim a wormhole was found. It claims the data is consistent with one. That is the language of rigorous science applied to the edge of what is currently knowable. But edges are exactly where discoveries happen. And this particular edge is one that, if the signal turns out to be what the most striking interpretation of it suggests, would rank among the most significant moments in the history of human knowledge. Not just a discovery about physics, but a first contact of sorts with evidence that our universe is not the only one, that something exists beyond it. And that on an ordinary Tuesday morning in 2019, a ghost of that something brushed past our instruments, left a trace in the data, and waited 6 years for someone to look closely enough to see it. To understand the full weight of what is being proposed, consider how long wormholes have lived as a mathematical concept without ever being connected to actual observational data. Since 1935, they have existed in the equations. Since the 1960s and 1970s, they appeared in theoretical discussions of spacetime topology. Since the 1980s and the work of Morris and Thorne, physicists had a framework for thinking about what it would take to make one traversable. For 90 years, the wormhole has been one of the most famous structures in all of theoretical physics and one of the most frustrating because every time the theory advanced, the experimental side stood completely empty. No candidate signal, no observation, no data point that could be pointed to and examined against the mathematics. GW 1990521 changed that for the first time, not conclusively, not beyond scientific doubt, but for the first time in 90 years, there is a real measurement, a real detection recorded by a real instrument, sitting in the scientific literature alongside a mathematical model that describes it as a possible wormhole signal. The gap between pure theory and observational physics, which has yawned open for nearly a century in this field, has narrowed, not closed, but narrowed in a way it has never narrowed before. The debate around the black hole information paradox makes this even more significant than it appears on the surface. The information paradox is the problem of what happens to information that falls into a black hole. Quantum mechanics says information cannot be destroyed. This is not a philosophical preference. It is a mathematical requirement built into the foundations of quantum theory. But when something falls past the event horizon of a black hole and the black hole later evaporates through Hawking radiation, where does the information go? If the Hawking radiation is purely random thermal noise with no imprint of what originally fell in, then the information is gone forever, and quantum mechanics is violated at the most fundamental level. This problem has sat unresolved at the center of theoretical physics for 50 years. The ER equals EPR conjecture offers an approach to solving it. If the particles that escape as Hawking radiation are quantum entangled with particles inside the black hole via the wormhole structure that entanglement creates, then information is never truly trapped. It is encoded in the correlations between the inside and the outside, in principle, recoverable. The Einstein-Rosen caterpillar finding from October 2025 strengthens this picture significantly. The wormhole connecting entangled black holes remains stable and geometrically consistent, even under the chaotic conditions of real quantum entanglement. It grows longer, it deforms, it develops bulges and irregular segments, but it preserves the connection and the firewalls was predicted at the event horizon that many physicists expected would destroy anything approaching simply do not appear in the models. What this means for the GW 1900521 question is subtle but significant. If the ER equals EPR picture is correct, and if entangled black holes are routinely connected by wormhole structures, then the scenario proposed by the 2025 research team is not nearly as exotic as it sounds. Black hole mergers happen constantly across the universe. If even a fraction of those black holes are entangled with black holes in other regions of spacetime or in other structures beyond our universe, wormholes connecting our universe to those regions are a natural consequence of the quantum structure of gravity. And if those wormholes can transmit gravitational wave signals, then the data we have already collected may contain multiple instances of this phenomenon, unrecognized, waiting for the right framework to make them readable. The team behind the 2025 paper flagged GW231123, most massive gravitational wave event ever detected, as a potential second example. It shares the same critical property as GU90521, a short burst-like signal missing the inspiral that should have been present at its mass. If anomalous events like these accumulate in the data over the coming years of increasingly sensitive observations, the statistical pattern will either strengthen the wormhole hypothesis or reject it. LIGO currently detects a gravitational wave event roughly every 2 to 3 days with its upgraded sensitivity. That rate means the data accumulates fast. The question of whether these anomalies are real, whether they cluster, whether they match the predictions of the wormhole echo model, will become statistically answerable within years rather than decades. What began as an anomalous detection on a Tuesday morning in 2019 has become the focus of one of the most genuinely open questions in contemporary physics. Not because the answer is known, because for the first time, the question is scientifically approachable with real data, real instruments, and a theoretical framework that is becoming more robust with every new study. The data exists. The tools are developing. The mathematical foundation that could explain the anomaly has survived its first serious experimental tests. And the possibility that a gravitational wave signal from a black hole collision in another universe passed through a wormhole and into our detectors cannot be dismissed by anything currently known. That is where science stands on this today. Not at a confirmed answer, but at the edge of one. And in the history of physics, standing at the edge with the right tools has always been the moment just before everything changes.